Okay, these are some mass on a spring optional problems. Alright, a mass oscillates from the end of a vertical spring. So it's hanging like this. And what may be done to increase the frequency of the oscillation? Okay, so period of a mass on a spring, is 2 pi times the square root of m being the mass value, over k. K is that spring constant. We talked about that when we looked at elastic potential energy. It's a measure of the stiffness of the spring. So if we want to increase frequency, and this tells us we have two answers. Remember, frequency is 1 over period, period's 1 over frequency, so they're related to each other. Amplitude is not included in this equation, nor is gravitational field strength. So we know the answer is going to have to do with mass and spring constant. If I flip this to get frequency, because period is 1 over frequency, frequency is 1 over period, then I've got, this will be flipped. And if we look at these answer choices, if I increase this value, I would be able to increase the frequency. So now, let's just write this out. This is going to be 1 over 2 pi over m over k. It looks really messy. But imagine I'm flipping this now. Okay, so if I increase the spring constant, that's going to make my frequency value bigger. So that's one of my choices. And then if I decrease the mass, now I've got a larger number on the bottom here. A smaller number on the bottom here, decreasing the mass, that's also going to increase my frequency. So those two things would increase frequency. Okay, mass attached to a spring, allowed to oscillate vertically, which would not change the period. Again, going back to this equation, I see here I've got some answer choices with amplitude. That would be a no. Gravitational field strength, even though these two also include items that are in that equation. This isn't in that equation, so I'm really left with choice 1. And if you think about doubling the mass and doubling the spring constant, you're going to get the same thing because the twos cancel. So if we doubled both of those, we would be left with the same period value as we had before. Okay, period of a mass on a spring system is doubled while still using the same spring. Okay, so that means our K value, our spring constant, is not going to change. By what factor does the frequency increase or decrease? Okay, so if we double period, so period is 1 over frequency. Frequency is 1 over period. If I double period, now my frequency is going to be a factor of 1/2, because those are inverse of each other. If one of them goes up, the other one's going to go down. By what factor does the mass attached to the spring increase or decrease? This is if the period is doubled. Okay, so if t is now 2t, so we have 2 times 2 pi m over k. How could we double it by changing mass? Okay, so if we multiplied mass by 4, that would put a 4 underneath this square root. So So if m equals 4m, then we would have 2 pi 4m over k, and that would equal, that 4 would come out of the square root, and so then we'd have 2 times 2 pi times m over k. So if we increase mass by a factor of 4, then we can double the period. So m increased by 4x, okay? Because we're not changing the spring, and 2 pi is just a constant, so. Okay, we've got a mass hanging on a spring with a given spring constant. It oscillates with this constant amplitude, so that means as it goes back and forth through equilibrium at its max displacement, it's 12 centimeters. What's the maximum acceleration of the system? Okay, so let's see, let's write down a couple of things. Newton's second law, we can use this here to help us out. For springs, our F net is going to be the spring force, which is our minus k times x. That's our restoring force for the spring. This is also known as Hooke's law. So k is our spring constant, x is our displacement. I could set that equal to m times a and solve for acceleration. So I have minus, my spring constant is 12 newtons per meter. My displacement, my x here, is 12 centimeters, so I need to convert that to meters, so that's going to be 0.12, and then I've got 0.4 for the mass and a for the acceleration, and let me solve for that and see what I get. I have my other calculator. Let's see. 12 times 0.12 equals, divided by 0.4, gives me 3.6. Let's see if that's one of the answer choices. Oh, how fortuitous. 3.6 meters per second per second. And note that that says max acceleration. Acceleration is not actually a constant value with a mass on a spring. Same with the pendulum. So they're not objects where we have constant acceleration. Okay, spring mass systems set in oscillation. So we've got 4 different systems here. One, hard to read those. Oh yeah, 1 and 3 have twice the mass of 2 and 4, and then 3 and 4 have twice the k value, and so we want to rank the period. Okay, so our period again, 2 pi square root of m over k. Okay. So this is a ranking type question. So, all right. So let's see. So 1 and 3 have twice the mass of 2 and 4. Oh, yeah. Hang on. I'm trying to see how to write this so that it makes sense. So if I have 1, so what I'm going to do is I'll have my period equation in here, and then I'm going to have factors within each of those, depending on the mass and the spring constant values. Okay, so 3 and 4 have 2 times 1 and 2 for the spring constants. So these are my 2 spring constants. So I'll say these are a 1, and then these are a 2, because 3 and 4 are 2 times that. Okay. And then 1 and 3 have twice the mass of 2 and 4. So I'm going to put a 2 there for 1 and a 2 there for 3. Okay. Okay, so if I go back and rank these, look at these, 2 is going to be the greatest. No, 1 is going to be the greatest. Yeah. Something's not making sense here. Sorry. I'm confusing myself. Let's see. Alright, let me look at this one and I'll start back with it in the next video.